with a brief introduction here. My name is Chris Johnson. I'm a project engineer at Experior Laboratories. I joined Experior about 2 years ago, originally as an instrumentation engineer. I was designing and building control and data acquisition systems to support the various qualification and acceptance test programs that would come through the doors at Experior. And let's see if the clicker works here. There we go. For those of you who haven't heard of us, Experior Laboratories is a third-party general test laboratory. We provide independent design qualification and acceptance test services from everything to vibration and shock testing, and we'll get into that here in a little bit. So, we help a lot of the component system manufacturers in the LA area, mainly in the space industry, but we do a lot of testing for different industries from automotive to train components and assemblies. So like I said, our specializations actually in dynamic testing. So it's things like sine and vibration testing, including vibration and temperature, shock testing, thermal vacuum, and different types of environmental tests. And we have a wide variety of different types of chambers at our facility to incorporate full qualification programs. Our Oxnard location is roughly 40,000 square feet, spread across 3 different buildings. I've been kind of moving through and showing you some images of some of the different test systems we have at our facility. The upper right-hand image here is a horizontal shock machine. So it's used to test large and heavy test articles. It actually slides across that rail there and then hits a brake at the end. And that impact forces a high shock impulse into any kind of structure or test article. Down on the lower left-hand corner here, we have a thermal vacuum chamber. And on the lower right-hand corner, we have our KIPS machine, which is a kinetic impact pyrotechnic shock simulator. And we're going to get to that in just a little second, talk a little bit more detail about that machine. So we've been recently seeing this trend in the space industry where we're really seeing a quicker push for quicker time to market for a lot of the products coming through our facility. So that flows down into the testing world. We're seeing a lot of our customers with accelerated test programs. So they're coming through the gates needing to expedite pretty complex test programs. So today I'm just going to walk you through what a typical high-velocity program looks like at Experior. And to do so, I'm going to follow along a previous program that was aimed at qualifying 3 types of fluid control valves. Our customers supplied 3 types of fluid control valves that were put into groups 1, 2, and 3, and each group had 3 identical test articles. So there was, all in all, a total of 9 test articles moving through the test matrix you see here. And we were testing to the RCC 319-14 specification. So in addition to the qualification test levels or tests you see here, there was functional and ATP tests performed before and after each one of these qual environments to verify there was no degradation in performance as a result of exposure to these qual environments. So we're going to just touch on a few of the big ones here, a little bit more exciting than the bread and butter of what we do at Experior, which is random vibration, shock testing, thermal vacuum, and life cycle testing or fatigue testing. So a little bit about vibration testing for those of you who aren't familiar, just a brief background. We do vibration testing to ultimately simulate environments or test the structure, the structural integrity of a test article. So sine testing is used usually to sweep through a series of frequencies at different levels and ultimately find a resonance in that structure. Sine dwells on that particular resonance frequency to do fatigue testing to see how long you can vibrate this structure at a particular frequency until it breaks. That's some really important information to know. Next up is random vibration, and this is more aimed at actually recreating a simulated environment that you would see in real life. So for random vibe, a big one is a launch environment, obviously for the space industry, where you have heavy shaking and random vibrations at all different frequencies. So we have a way to simulate that in a laboratory environment using an electrodynamic shaker, which is the industry standard for vibration testing. It's essentially, you think of it as a big speaker, honestly. It's, you send a drive signal into a power amplifier, and that feeds into an armature that has a motion analogous to a speaker cone. And in the upper right-hand corner here, those are some of our largest shakers, and they can support payload up to 8,000 pounds. So we have quite a range of size of shakers from the component level to subsystem level. So here's a short video just kind of illustrating the maximum capabilities you can get out of some of our larger shakers. These are actually used in tandem, so you can essentially double the force rating that these shakers have, which is 40,000 pound force. So this is one of the first tests we actually ran on these shakers. Obviously it's in the vertical direction. If you wanted to test at different axes, you would actually rotate the shaker armature 90 degrees, and you would attach a slip table, which is just a vertical plate basically, and you can rotate your part to test in the horizontal axes. And that was a large train assembly that we tested at the later part of last year. So moving back to that qualification program of the fluid control valves, if you take a look at the table on the upper left-hand corner, it shows the minimum qualification levels that we are actually testing to. And you can see it's fairly low compared to the maximum capabilities that we currently have for some of our equipment. So we had quite a bit of headroom to kind of play with different test strategies, and we ended up being able to come up with a concurrent strategy to test multiple test articles at once, which for our customer who is in the hurry to get this test program finished and out the door, it was a great advantage to us. So we were able to actually test valve groups 2 and 3 in one test. You can see there are 6 valves here that are kind of blurred out in green. They're mounted to what we call a vibration cube, which is a standard cube fixture we use to standardize our test design fixturing. It allows us to just design a simple adapter plate to customize any test article to that cube, in which we can machine in-house and is fairly quick. And then on the upper right-hand corner here, you see the larger valves, which we tested individually as their group. Obviously, they were much heavier, so we couldn't fit all of those on a single cube. But we got that down to 2 runs of vibration, and as opposed to 9 individual runs. We then rotate the valve 90 degrees and test all 3 axes for 1 hour each. So next up is shock testing. This is another one of the cornerstones of capabilities we have at Xperia Labs, which is high G shock testing. And similar to vibration, it's another form of dynamic testing. In this case, it's simulating a short impulse shock event that then spreads through a structure, and it is emulating things like a stage separation or any type of pyrotechnic event, anything that's a short duration, high G level. And there's different types of ways you can simulate this in a laboratory setting. Pyrotechnic shock simulators like I showed you before, which we'll get into a little bit more. Mechanical drop tables, horizontal shock, and even live pyrotechnic shock events are all ways you can utilize to simulate this environment. So here's a short video of our KIP system in action. This is one of 2 of our systems here. This was designed to essentially fire a steel or aluminum projectile at a resonant beam, and that shock wave would then travel through the beam into your shock fixture, which is another cube in this case, and then ultimately into your test article. And you're monitoring for acceleration on the control side, which is essentially your input to your test article, as well as response, which is an accelerometer mounted on the actual part, and you can see the differences, and if there's a high resonance, you will pick that up in your response. So here it is in full speed. You can see it's a pretty short event. It fires off, hits the beam, shakes a little bit, and settles. Watch that again in slow motion here. You'll see that projectile come up, hit the beam. You'll see a few of the major modes of the structure, and even some secondary side modes, which we monitor sometimes as well. We call it crosstalk. And if you have strange crosstalk, that's usually inherent of bad fixturing, and that's some of the challenges that come into designing the fixturing. All right, so coming back to our qual test again, for this test for the shock environment, the peak levels was around 1,300 Gs. So actually we utilized our shaker and our KIP system in this case. Again, testing in parallel to speed things up and cut down test setup and test duration. We were able to test valve groups 2 and 3 on our shaker, call it shaker shock. The larger test article had to be done on our KIPs because of its mass. There was limitations with reaching the 1,300 Gs we needed to achieve that minimum qual level. All right, and then moving into thermal vacuum testing, valve group 2 was the only test article that had to go through thermal vacuum testing. It was a solenoid valve electrical mechanical test article. So the goal intent of this test was to pump down the chamber, ramp it up to its minimum and maximum extreme temperatures, and execute a performance test. So test for things like leakage, flow, and actuation at vacuum. So you can see the setup photos here on the right. You can see the test articles. Again, they're the green blurred out images, and they're mounted to what we call a thermal platen, which allows us to control temperature in a vacuum by using conduction. So there's some thermal resistive heaters and LN2 tubes running through to heat and cool the device using conduction. So we had to design some custom pressure fittings to run through the chamber pass-throughs to allow high pressure to flow through the valve during the test, as well as some thermocouple wires and electrical wires to control the actuation and monitor temperature data. And then last but not least is the actuation life cycle. And the intent of this test was pretty straightforward as well. Each test article was to undergo 500 cycles of actuation, and performance tests were executed before and after to see if there's any degradation in performance as a result of exposure to a life cycle test. And so the schematic on the upper right is the test stand that we designed in-house. It is a fairly simple setup, but we mobilized it very quickly. We designed 3 nearly identical setups, but they're all slightly customized to each valve type, depending on the flow rates and things like that. They're a mobilized setup which supported our overall current concurrent test strategy, and we were able to put them together in less than 2 weeks with off-shelf components, which was supported the expeditious nature of the program. In addition to that, we added some automation capabilities to these test stands, so we were able to actually actuate these valves overnight and leave them unattended. So that greatly reduced, again, the test duration in a whole, and gave us some additional capabilities. So again, this was meant to be just a very brief high-level overview of what a typical fast-paced qualification program looks like at Experior, and how we're able to leverage our wide range of capabilities and high volume of test systems to meet our customers' demanding schedule requirements. If you're interested in reading a little bit more detail about this particular program, there's a link to the white paper. You can also come by our booth. I think we have some printouts there. I think with that, we can open up the floor for any questions.